Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. In this lecture, we are going to see the integrator and differentiator. First of all, we should know why are we going to learn the concepts like integrator and differentiator in this lecture. Actually, we have been discussing the concepts related to digital electronics in the set of lectures that we have been seeing now. We have dealt with the inputs like zeros and ones as far as the digital electronics is concerned. But how do we give the zeros and ones as inputs and take the values as outputs? They are typically in the form of voltage. The high voltage represents 1 and the low voltage represents 0. Actually speaking, we will give these inputs and take the outputs in the voltage form, but we will be normally getting the voltage forms as waveforms. So, the waveform generator is the topic to be learnt under digital electronics, which helps us to understand the functioning of various digital electronic circuits. So, this lecture is focused at the waveform generators. So, that is the generic title for today's lecture. Under that title only we are going to learn the integrator and differentiator. This is there in the curriculum. So, we are going to learn about the concepts of integrator and differentiator. So, let us see today's session outline before we actually start the topic. In this session, we are going to see the need for waveform generators, under which we are going to learn a differentiator and an integrator. What are waveform generators? In the earlier lectures where we learnt the concepts related to transistor and the functioning of transistor as different components in electronic circuits, like different ways the transistor acts. The transistor acts as an amplifier, the transistor acts as a switch. So, all that we have learnt. After that, we come across one small concept called oscillators. The transistors are also used as oscillators. They are capable of generating waveforms, varying waveforms. So, the waveform generator concept to some extent we have already learnt in the earlier lectures, and also the words differentiator and integrator are very familiar to us. We have learnt these circuits under the concepts called filter circuits, the high pass filter, low pass filter, band pass, band eliminator, like that various filter circuits we have learnt. So, what we are going to learn in this lecture is the application part of the waveform generators in digital electronics. So, we need to first know why these waveform generators are very important or crucial in understanding the functioning of the digital circuits. So, let us learn what are waveform generators and why they are necessary as far as these digital electronic circuits are concerned. So, let us have a look at the slide and learn why these waveform generators are important, and also what are the different kinds of waves we come across through these generators, and also we are going to learn which waveform is the most appropriate one for the digital electronics, the functioning of digital electronic circuits. So, let us have a look at the slide. A waveform generator is an electronic circuit used to generate electrical waveforms. These waveforms can be either repetitive in nature or single shot, that is once only, in which some kind of triggering source is required either internally or externally. The resulting waveforms can be injected into a device under test and analyzed as they progress through it. This would enable one to confirm the proper operation of the device or to pinpoint a fault in it. As far as the digital circuits are concerned, for a given input, we need to get an output, expected output according to the digital expression or digital circuitry. So, whether the circuit is functioning properly or not, how do we check? We need to give input and take the expected output. When we give the input, the output is taken in what form? It is taken in the form of voltage. The input too is also given in the form of voltage. And to get an understanding of this, we will be able to have a grip of the functioning of these circuits, mainly comprising of the gates as far as the digital circuits are concerned, and the working of these digital circuits for a given set of inputs. We will be able to have a grip when we have a look at some of the visuals. So, let us see what further we do have here. See, these are some of the waveforms. The first one is a sine wave. It is also called as the sinusoidal wave. It progresses with this variation. It is governed by the function sine, and this is a square wave which has only two states. This is a higher state and then a lower state, and this transition from higher to lower is happening suddenly. So, this transition is not at all highlighted here, but the two stable states are quite important for us. And this is a triangular wave in which the voltage is gradually increasing and it is linear also, and then gradually and linearly it is decreasing. So, this is a triangular wave, and this is a sawtooth. The voltage increases to a particular value and then again it starts from the lower value, suddenly it falls. So, it is called the sawtooth wave, or sometimes people call this as a ramp. So, these are the different kinds of waves normally we come across in electronics. But all these waves, will they be useful as far as the digital electronics is concerned? We need to learn more. So, let us see what are the waves which are useful for the digital circuits. See, this shows much more waves which are more or less compared to the square wave. When we have a look at this, this is a square wave, and this shows the triggering. Only the spikes, the higher and lower voltages are happening. They are called transient values. For a very short duration the voltage is high, after that it suddenly falls. So, this is referred as a spike, and here a low frequency response. See, this flat portion or the stable portion is getting altered. Similarly, here also slowly it is getting modified or deformed. So, all these represent the way in which the waveform gets modified. The footnote here tells what makes it get modified. Actually, this analysis is not too much required for us. Just I wanted to show you the different types of waveforms, because we have seen the most often used waveforms like sine wave, square wave, triangular wave, and the ramp, sawtooth. But apart from that, there are lots of other kinds of waves also we come across in electronic circuits. But what is the most appropriate wave that we normally use in digital circuits? So, we are narrowing down our requirement. Let us have a look at the slides further. The need for digital or square waves. In square wave, the amplitude alternates between fixed maximum and minimum values at a steady frequency with the same duration at minimum and maximum. The transition between the minimum and maximum and vice versa is instantaneous for an ideal square wave, but this is not reliable practically. Actually speaking, from the higher state to the lower state, when the transition occurs, it does not occur instantaneously, though we represent the instantaneous transition in the waveforms, but there is a small time delay involved in that, but that is not very much highlighted when the stable maximum and minimum states are of longer duration. The transition is not very much going to affect the performance of the digital circuits unless and until it warrants. We have some triggered circuits also in which the transition plays a major role, but right now the circuits what we see are not of that nature. They are just elementary digital circuits. So, the transition is not very much important right now for us. And why these square waves are important for digital circuits? They have the two states, maximum and minimum. That is what we need in digital circuits. We want a maximum value and a minimum value, high or low, the 0 or 1 like that, or ones and zeros like that. So, this enables us to opt for the square waves for the digital circuits. And do these waves, square waves, represent zeros and ones? Definitely they represent. When we have a look at the way it represents, we will be able to get a greater understanding of the digital wave, the square wave representing digital inputs. Let us see further. The square waves are often encountered in electronics, signal processing, and in general digital counters, digital clocked circuits, etc. Have a look at this diagram. This clearly tells us how a square wave represents zeros and ones. See here, it is quite often alternating between a higher value and a lower value. Here the higher value represents 1 and the lower value represents 0, and similarly here also. So, look at the way in which the stable higher and lower states are existing. It is for a greater duration. So, this is also a square wave, this is also a square wave, they represent the zeros and ones here also. So, the frequency of the square wave is also important, that governs which input it takes. See, actually when we have a look at this representation, it is nothing but a 4 input digital value, 4 inputs. See, this could be taken as A, this could be taken as B, this could be taken as C, and this could be taken as D. So, there are 4 inputs, one varies alternatively, another one varies twice, and another one 4 times, and another 8 times. So, this is a 4 input digital signal. These zeros and ones, if you could recall what we have learnt in the earlier lecture, the number of inputs we have will determine the set of combinations 2 to the power n. I hope you could recall what we have learnt in the last lecture. I would like to correlate this digital input to typical circuits in the coming part of the lecture. Before that, we shall have a short break. Welcome back. Now, we have understood how a digital wave is very much useful as far as the digital circuits are concerned. Here what I meant by digital wave, it is nothing but a square wave. The square wave very well is useful for giving the input for the digital circuits. Now let us have a look at a 3 input gate, any one gate we shall choose of our interest, and how the 3 input gate gets the input in the form of square waves. Let us have a look at the 3 input gate. See, this is a 3 input AND gate. A, B, C are the inputs and this Y is the output, and the input for A is varying in this manner, input for B is varying in one particular manner, and input for C is also varying in one way. So, do not give importance to the way in which the maxima minima occur, but this is what is given. What is the output wave? That is given as Y here, it is marked in green color. So, for various stages, various transitions, wherever this low to high or high to low transition occurs, they have considered the cycle like that, and we will get an output maximum only when all the 3 inputs are maximum. That is only possible in this range between in the third section only all the inputs are maximum, A is maximum, B is maximum and C is maximum, and for all the other sections any one is at a lower value or lower potential. So, we will only get the lower output. See how the zeros and ones are easily represented by the waveforms. So far we have used the zeros and ones for giving the input, but especially in this lecture we have learned how the inputs comprising of zeros and ones, but in the form of waves, square waves, how they could be given, we have elaborately learned in this lecture. So, the necessity for waveform generators is also warranted in this lecture. How do we generate the square wave or the triangular wave, etc., especially the square wave, because the digital circuits very much use the square waves. How do we generate the square wave? That is why the topic waveform generators is given for this lecture. So far I have taken the topic in this manner to emphasize why these square waves are important for digital circuits. Now we are likely to learn how do we generate the waves, square waves. We can generate the square waves using some complicated circuits, electronic circuits, but as far as our curriculum is concerned, we are supposed to use only the passive components. The passive components here, what we mean, they are the resistors, capacitors, only these, or maybe an inductor. So, these are all passive components, but active components means they will be using the semiconductor material. So, diodes, transistors are all coming under the title active components, but here we need to generate the waves using passive components. That is what is given in our syllabus, or that is what is mentioned in the curriculum. So, let us restrict ourselves to the two types of circuits, namely a differentiator and an integrator. Only the terminologies are different, but they are already known to us in some other words, like as I mentioned, they are called filters. So, let us learn how do we use these differentiator and integrator circuits to generate various waveforms. So, let us have a look at the slide further to learn more. See, here also one more example is given. It is an XOR gate. The XOR gate gives an output 1 when both are not the same. It is A B bar plus A bar B. So, any one has to be different from the other input. So, that is possible only for certain portions of the inputs. So, this XOR operation is also depicted using this circuit. Now, the differentiator. A differentiator gives the derivative of the input voltage as output. A differentiator using passive components resistors and capacitors is a high pass filter. The circuit is shown, it acts as a differentiator only when the time constant is too small. So, this is a differentiator, it is called RC differentiator. When you have a look at this RC differentiator circuit, we are actually reminded of the filter circuits that we have already learned in some of the earlier lectures. The differentiator is nothing but a low pass filter. It allows the low frequency input to pass through. For the high input, the differentiator puts up a huge resistance and blocks it. And another thing to be kept in mind about the differentiator circuit is its time constant is too small. When input is given with a very high, with a stable value for longer duration, the circuit cannot accordingly behave. It will immediately discharge. The capacitor that is used in the circuit will quickly get discharged as far as this differentiator circuit is concerned. So, let us have a look at the diagram once again and learn more about the differentiator circuit. See, when we give an input of a square wave, this is not generated, this is actually given to this circuit as Vi, and the output is found to be spikes. See, for this duration, the section CB, when we take, the capacitor quickly discharges the moment the higher voltage is given, because the time constant of this, the differentiator circuit is too small. It immediately, the moment the higher voltage is there, it immediately discharges, and similarly this is happening in the reverse direction. And once again, when the next pulse, next stable state comes, again the discharge is happening. So, a differentiator is identified by this test. When we give a square wave as the input, the output would be a spikes. Where do we need this kind of spikes? In some of the electrical digital electronic circuits, we may have to trigger some inputs. One input might be a particular value, the other input need not be a stable value, it should be temporarily at a particular value and come back. So, like that we call that as triggers. Triggers are very much used. There are some circuits called as triggered circuits. So, for those kinds of circuits, we will normally use a spike waveform, or they are called the trigger waves. They are also called clocked waves because they are happening at a particular sequence. So, they are often referred as clocked input. One input will be varying in one fashion, the other input is connected to the clock pulse or the spikes what we have got as an output of a differentiator when the square wave is an input to it. So, this clock signals will sample the circuit at a particular fashion, and the output is taken. So, that is very much useful for the digital circuits. So, this is a waveform generator. When we give a square wave as input, we get the clock pulses as the output. So, this is one waveform generator we could keep in mind. What about the other outputs for various inputs? What are the other inputs we will be other outputs we will be having? So, let us have a look at the inputs and outputs for the differentiator. The differentiator actually differentiates. The voltage at output is proportional to the current through the capacitor. The current through the capacitor can be expressed as C into dV by dt, and the output is taken across the resistor. So, the output will be RC because the resistor is to be multiplied. This is the current only. So, we need to multiply with resistor to get the voltage, and when we have a look at this expression, the dV by dt comes, which is nothing but a differentiation operation. So, we call this circuit as a differentiator. When various inputs are given, the differentiated outputs are obtained. So, let us have a look at the waves, what we give and what is expected at the output of the differentiator. So, this gives us a clear picture. When we give a sine wave, we are likely to get a cos wave. There is a phase lag in this case. So, we get a cos wave, which is nothing but the differentiation of sine. Similarly, for a square wave, we get spikes, and similarly for a input of triangular wave, we are likely to get an output of square wave. So, square wave is also possible output in the case of differentiator, provided we give a triangular wave as the input. In the case of triangular wave, there is a gradual increase is happening. So, for this increase, this voltage remains constant because it is getting charged. The capacitor is getting charged for the increasing steady increasing input. So, that is why it remains constant, and after that the triggering occurs. So, there is a sudden fall in the value like that. If we keep the RC value in mind, it has got a very small RC value, the time constant value. So, accordingly the circuit is behaving for the given input. Now, we can generate square wave also using a differentiator, provided we give a triangular wave as the input to it. Now, it is time for us to learn the application of the differentiator. See here, when a square wave is applied at the input during the positive off cycle, the capacitor charges. So, initially the voltage across the resistor will be the applied voltage. As the capacitor charges, the voltage across the resistor decreases. Now, the other circuit, which is called the integrator, that also quickly we will learn. What is an integrator? Well, let us see. The integrator also uses the passive components R, resistor and capacitor. See, it is a low pass filter. Here the time constant of the circuit should be very large. Here the output is taken across the capacitor. Let us have a look at the circuit itself. This is a circuit. This is an RC integrator. For a given steady value, because the RC value is very large here, the capacitor keeps charging. Even if the input is steady, the capacitor keeps charging because of the high time constant, and we get the triangular wave as the output. Similarly, we have various waves. For a square wave, we get a sine wave because of the higher time constant value. Similarly, for a triangular wave, we get this as the output. So, this one, for an input of square wave, we get triangular wave as the output. For an input of sine wave, we get the minus cos as the output, because that is the integrated value. The previous slide says that during the negative off cycle, the capacitor starts to discharge and comes to 0. This appears as the slow and steady fall in the voltage in the output. This process repeats for the remaining cycles and a triangular wave is obtained. This is actually explained for the integration property of this circuit. Now, it is time for us to take a small test. Let us have a look at the slide. See, when a square wave is given as the input, when we have an integrator circuit here and a differentiator circuit here, and when the outputs are fed to the CRO, cathode ray oscilloscope, which has a display, what will be the outputs? Here the question marks I have asked. We can make a guess very easily, because this is a well known input. See, this will be the output, because the first one is an integrator circuit. The integrator circuit will produce a triangular wave when the input is a square wave, and again the differentiator will produce an output of square wave for a given triangular wave. See, the integration and differentiation are complementary operations. So, the given input is obtained as the output. So, this is a wonderful exercise we could do with the CRO and the circuits. Now, it is time for us to look at today's summary. In this session, we have seen the need for waveform generators. We learned two waveform generators like differentiator and integrator. Let us test our understanding by answering these questions. Explain the need for square wave in digital electronic circuits. Explain the working of a RC differentiator with inputs and output waveforms. explain the working of a RC integrator with different input waveforms and their outputs. So, with this I would like to wind up today's lecture. Let us see the other concepts in the forthcoming lectures. Thank you for listening.